Going live. It says I'm live. Excellent. And we're back on. Okay. A couple of reminders. First and foremost, I had a major assessment due today, and I realized this morning that in the directions to the Google Classroom assignment, I put 7 a.m. But then when I actually figured out, actually clicked, I don't know why, it was like muscle memory. I put it for 2 p.m., which I realized looking at the number of people who have submitted it, perhaps there was a little confusion. Maybe they didn't look at the exact directions, but looked at the actual assignment time. So I'm going to say that's on me. And if you do turn it in before 2 p.m., it would not be considered late because that's what the Google Classroom assignment says. So please make sure you're paying attention to that, because I did see how many people had turned it in versus had not turned it in. So we'll get there. Next, we are going to be starting a new unit today on probability, which is a major component of statisticals. I wanted to say statistical analysis and statistics at the same time, but it did not work out, and it became like icicles. Regardless, it's been a long weekend. Goodness gracious. When we come back from break, how many weeks until midterms? Yeah. I don't know what the midterm schedule is per se. Some years, like now, mind you, it's going to be the 25th, starting on January 25th. But some years they've done, okay, we'll do the B-Day classes first. Okay, why? I don't know. It just happened to fall on that day. In fact, what color day is it supposed to be? I don't think they actually have it on there. Oh, yeah, that calendar's messed up. Yeah, that calendar's a wrong calendar, so I can't go by that. So whatever. I've seen some years where they've done like periods 3 and 4 first. I'm like, that's dumb, but that's what they do. So once the schedule comes out, I'll let you know as soon as possible. But yes, there are 3 full weeks when we get back in January. Oh, goodness. Do you realize like every school that is kind of like surrounding us right now is going virtual? Yeah. It's just so crazy. I don't know. But anyway, I'll keep my opinions to myself, even though it's probably... Anyway, shut up. Now, as for today and Wednesday, I need to introduce to you probability. Because of the circumstances of seeing some of you guys only once a week in September and October, obviously some things did fall a little bit behind. Currently, right now, what is today, the 21st? We're only exactly 1 week behind the pace that I wanted to set from previous school years, which is not too bad, but I would like to catch that up. I do have plans for that. We'll figure that out. But as for today, we are going to be starting with a bit of probability. Now, first, why was statistics first studied as a mathematical subject? Take a guess. Why do you think statistics was first studied as a mathematical subject? Kind of. They had more nefarious means, though. To cheat at gambling. I'm not even kidding you. To cheat at gambling. That's why statistics first became a mathematical subject. Now, personally, and this is the honest truth, I hate gambling. I hate gambling. I hate the concept of Vegas. I hate the concept of Atlantic City and its casinos. I hate everything about it. I do not bet on things. I do not wager money on things. That being said, I know a lot about gambling. The reason for that is because my dad, when I was a kid, had a bit of a gambling addiction to the point where I was the only 8-year-old who knew how to do a wheelhouse bet at Monmouth Racetrack. One time, my dad had enough money to get into the Atlantic City racetrack. He had enough money to get for, I'm sorry, let me rephrase. He had enough money for him to get in, and he had enough money to gamble with, but he didn't have enough money for me to get in. So what did 8-year-old me do? Well, my dad had me scale a fence and meet him on the other side, so he didn't have to pay for me to get in. It's just one of those things. You guys ever smell like cigar smoke? You got like a waft of cigar smoke? Whenever I smell cigar smoke, it takes me immediately back to the racetracks that my dad took me to when I was a kid. You guys know what an OTB is? off-track betting. You go to an OTB, which is basically a glorified bar, and you watch these races on television screens from across the country. It's ridiculous. But that's what we did. That's what we did. But that's how I first got into mathematics, because my dad, well, he wouldn't tell me what to how to actually understand the odds. I had to figure them out for myself, basically. It was really interesting. But I digress. We're getting into probability. In Algebra 2, you might have hit upon a little bit of probability. In Algebra 1, maybe a little bit. In middle school, maybe a little bit. It's been like smatterings here and there of basic probability. My intention for the next little bit of time is this. I want to recap and review some of the previous information of probability that you need to know moving forward, number one. And number two, I need to deep dive a little bit farther into some of the formulas and notation that you're going to be seeing during the course of this unit. I am so very excited. I enjoy probability so very much. I abhor gambling. I do not promote gambling whatsoever, but I do know how to cheat at most of it, just because it's great. You ever play poker? It's a very disgusting habit to play poker, but I know how to play it very well. Anyway, I'm in need, if you do not already have them out, those notebooks out and open. If any of you run into my dad in the public, I immediately apologize, because my dad still lives in Barnegat, where we grew up, and he tells me all the time, "Oh, Jim, I ran into one of your students," because he's got a little bit of a Brooklyn accent. Well, a major Brooklyn accent. Anyway, he's like, "I ran into one of your students." I'm like, "Dad," and he's just like, No. I saw this person. I was just like, "Hey, do you go to the high school? Do you know Mr. Maki?" I'm like, "Oh my gosh." Has any of you actually had that conversation? I'm being serious right now, because he's done it 100 times. I'm like, "Dad, you can't just go up to teenage girls and say, 'Do you go to Barnegat High School?'" Gosh. But he does. The man is 81 years old. If you ever met an 80-year-old, they pretty much do whatever the heck they want. Anyway. This is probability. Now, I believe this introduction is chapter 13 in your textbook. I believe it's chapter 13. 10, 11, 12. Yeah, I'm pretty sure it's chapter 13, because 10, 11, 12 was the first unit that we did during the course of the school year, and now we're in this unit on probability. Fun! Okay. First, a little bit of notation. Whenever you see the P parentheses with something on the inside, they are referring to the probability of an event. More specifically, the probability of event A. Now, it doesn't matter what that A is. I mean, obviously, it'll change the answer, of course. But it could be written as anything. It could be written as a sentence. It could be written as some other mathematical notation. But it describes an event, and you're looking for the probability of that event happening. This acts very much like function notation, f of x. Same concept. Now, over the course of time, you're going to be seeing various probabilities being presented to you in different ways, and some of these probabilities are going to be theoretical, and some of these probabilities are going to be experimental. Let me write down these, and then I want to go into a little bit more detail about that. First of all, a theoretical probability is what could happen, or what we believe will happen. Something very basic to that could be like flipping a coin. When you flip a coin, you expect or you believe that depending on however many times you flip that coin, that you're going to get approximately 50% heads, 50% tails. That's what you believe will happen. That's what could happen. But very often than not, when you actually put that into practice, maybe you get 50-50, but more often than not, you get something a little bit off of 50-50. Experimental probability is literally what did happen. Now, they're not always going to label these probabilities as theoretical and experimental. You're going to have to take the context of the situation, and make that determination. Let me see here. I wanted to bring up the Google Classroom on my phone so that I could actually see if there were questions or comments in the chat, but I'll move forward with this. There's a story of a guy who was locked in a prison cell in, I want to say, like the 16 or 1700s. And this guy, I don't know, it's like he did some kind of crime that landed him in prison for life. So, sucks to be him. And the only thing he had to pass the time, the only thing he had was a coin. And mind you, this is like a prison cell where it's like stone walls, like a little tiny window up here that he can't reach, like a hole in the ground for him to, drop stuff, and a giant metal door where they could like slide food through. There was nothing else. He had to sleep on the rocks. So he was in there for like 30 some odd years, and the only thing to keep his mind off things was, well, he had a coin, and he flipped that coin, and he would record his results on the wall. Problem is, nobody knew this until he died. Because once they realized, oh, he died, they had to come in, take the body, toss the body out because he's dead now. Mind you, it's the 1700s. They don't really care. But then across the walls, you could see like little tally marks that he made using the coin, keeping track of his results over the course of 30 years. And what happened over the course of 30 years was that the experimental probability, what actually did happen, wavered a bit, back and forth, back and forth, back and forth, above 50%, below 50%, above 50%, below 50% in terms of, let's say, like the percent of tails or something like that. But then over the course of the long run, it eventually flattened out. Well, he didn't track that. Mathematicians went in afterwards and actually like documented his findings. It was really interesting. My point is this. There is this concept known as the law of large numbers. And I'll give you a better illustration of it in a moment. As the number of independent trials increases, the long-run experimental probability, which I'm abbreviating just because I really feel like abbreviating today. The long-run experimental probability approaches theoretical probability. Where's my coin here? I have a penny. So I'm just kind of holding it for visual sake, but I have a penny. Now, this penny, if I were to flip this coin 10 times, let's just say 10 times, I'll actually do it here. Oh, no, I dropped it. It didn't count. If I were to flip this coin 10 times, how many heads and how many tails would you expect to happen? 5 and 5, yeah. That's what you would expect to happen. Theoretically speaking, I haven't actually flipped this coin, but what I think will happen is I will get 50%, 50%. If I flip it 10 times, I expect or I theorize the fact that it will be 5 and 5. Now, I might get 5 and 5. I absolutely might get 5 and 5. I might not get 5 and 5. But if I were to flip this coin, hold on, I'll keep track of tails. So I got a heads, that's the tails, it's 1 and 1, 2 and 1 heads, 2 and 2 tails, 3 and 2 heads, 4 and 2 heads, 4 and 3 tails, 5 and 3 heads, 5 and 4 tails. Oh no, that was a heads. 6 and 4 heads. It didn't get 50-50. Oh no, I guess the coin is broken. If I got 6 heads and 4 tails, would you expect that this coin is broken? No. What if I flipped it 1,000 times and I got 600 heads and 400 tails? Is the coin broken? Or I'm sorry, let me rephrase. Do you now have evidence to suggest that the coin is broken? You technically do. The more trials that actually happen, according to this definition right here, as the number of independent trials increases, the long-run experimental probability should be approaching theoretical probability. If I flip it 10 times and I get 60% heads, you're like, no big deal. Even if I flipped it 100 times, if I flipped it 100 times and got 60% heads, it still maybe is not as big of a deal. But if I flipped it like 1,000 times or 10,000 times and I'm still getting 60% heads, something's up with this coin. And you actually would have mathematical evidence suggesting that maybe either the coin is rigged or it's off balance. I don't know, but something's going on with it. The general idea is that the more trials that you conduct, the closer and closer and closer that this experimental probability should be approaching theoretical. It kind of looks something like this, where it's like there's 100% heads and there's 0% heads. And we're expecting 50%. When you start these trials, it might be like, oh, I got a heads. And then I got a couple tails in a row. And then maybe I got a little streak of heads. And then it went back and forth and back and forth and back and forth, back and forth, until eventually the long-run experimental probability begins to approach that theoretical at 50%. That's what we would expect to happen according to this law of large numbers. Question. Theoretically speaking, and I'm being very precise with my language, theoretically speaking, could I flip this coin 100 times and get 100 tails? Yeah, theoretically speaking. It's not likely to happen, but it could happen. It could, theoretically speaking. It's not likely to happen, but that's just what happens. Just one of those weird things. Now, if I were to flip this coin 100 times and I got tails, 100 times, on the very next flip, on the 101st flip, what are the chances of me getting a tails? It's still 50-50, as long as it's a fair coin. It's still 50-50. This is another generalization of the law of large numbers. They are independent trials. Each trial is independent of the next. The previous flips of the coin do not affect the next flip of the coin. If you were playing a game against someone, I don't know, let's just say you're like, in elementary school or some junk, and you're betting money on something, like, again, flipping a coin. I don't know. Or maybe you're playing rock, paper, scissors. I don't know. Something very basic. And you lose. You lose all these games in a row. And an outside observer kind of walks up and like, man, he should win one of these times. Man, he's due, isn't he? There's no such thing as being due. Someone might say, this guy should win eventually. It's the law of averages. I'm sorry, there's no such thing as the law of averages. If they're independent trials, then the probability of a certain event happening should remain the same each and every trial. It's not that if you lose a bunch of times in a row or win a bunch of times in a row or get a certain result a number of times in a row that the probabilities change, or they magically be like, well, Eventually, it's got, it's law of averages. Who's in trouble? Isn't she virtual? Okay. Okay, bye. That was fun. Okay, back to this. Let's see. Here we go. There is no such thing as the law of averages, despite the fact that people keep saying that there is. No such thing as, quote, being due. They usually say this kind of thing in like someone who's like plays baseball or something. Oh no, it fell. They usually say this kind of thing for someone playing baseball, where it's like, oh, this guy's like, a career 300 hitter. That just means that, for the most part, he gets a hit 30% of the time. And, oh no, the last like few games in a row, he's gone hitless. Man, he's due. No, he's not. Each at bat, theoretically speaking, each at bat, he has roughly a 30% chance of getting a hit if he is a career 300 hitter. There's no such thing as being due. It doesn't mean that it's like on the next at bat, he has a higher chance of getting a hit just because he's been in a slump. That doesn't mean anything. The law of averages is a myth. There's the law of large numbers, but not the law of averages. They may throw problems at you like that, where they word things in such a way where you have to identify it as one or the other. Let's see. No, I'll put this on the next page. Probability, you can measure as a decimal or as a percentage or something along those lines. Probability can be measured between 0 and 1 for fractions or decimals. It can be measured between 0 and 1 for fractions and decimals. Between 0 and 100 for percentages. Typically, we are going to try and stick to decimals. I don't like expressing probability as a fraction, simply because if I gave you the fraction 7/8 and the fraction 16/17, some of you might be able to immediately figure out, okay, which one has the higher number, 16/17 or 7/8. Again, some of you can probably do that in your heads or just figure it out logically. But if I just gave them to you and said, pick one now, you're going to be like, what? But if I gave them to you as decimals, and I said that you have this percent chance of something happening, if I actually gave it to you as a decimal, 16/17 versus 7/8, now you know immediately which one is bigger just by looking at the decimal. So I'm just letting you know that when we measure probability, yes, you technically could write it as a fraction, but we're going to prefer that you write it as a decimal because it's much easier to compare these numbers once they're in decimal form. Although, again, some problems may try to mess you up that way. It's pretty fun. I mean, for me, not for you. Mainly for me. So, for example, I don't know. I'm just going to give you some ridiculous example just to kind of give you like one end of the spectrum or the other. So the probability of flipping a coin. So you flip a coin and get heads or tails. Don't be one of those people that tries to tell me that it could land on its side, because you would be wrong. Oh, Mr. Murky, I saw a video on YouTube. Really? You did? Great. The probability of the coin landing on its side is so astronomically low that it is essentially considered 0. So if I flip a coin, what is the probability that I get a heads or a tails? It's 100%, but I'm not going to write it as a percent. I'll write it as a 1. Because it's guaranteed to happen, essentially. It's essentially guaranteed to happen. 50% of the time you get heads, 50% of the time you get tails. So together it's 100%, but I'm going to write it as a decimal. So the probability, let's just say, of you draw a card from a standard deck, which I'm going to have to get into cards in a little bit. But you draw a card from a standard deck of cards and get watermelon. You draw a card from a standard deck of cards and you get a watermelon. What are the chances of that happening? 0. Yeah, it can't happen. Mind you, I said standard deck of cards. Standard deck of cards. Not one of your like fancy whatever cards. I don't know. 0. Now, mind you, they usually specify that it's a standard deck of cards or something along those lines. Sometimes they might not, but, you know, it's like one of those things. And again, I'll get into cards in a little bit. I wanted to spend this first bunch of time going over notation and basic definitions because this is the stuff that it's like, oh, yeah, I learned some of this stuff back in the day, but it's like, it's been a minute, you know. What is a compliment? This is your opportunity to give me a compliment. No one jumped at that. So you all have lost 5 stars. You jerks. How about this? You've all taken geometry, right? And when I mention the word geometry, you get that chill up your spine. What is a complement in geometry? Yes? 90. What does it mean? Give me more. It's not just that it's 90 degrees. Yeah? Yes, 2 angles where their sum is 90 degrees. Did your teacher ever show you this where they're talking about, hey guys, complementary angles, 90 degrees? Yeah. And supplementary angles, you know, where it's like 180? Yeah, I don't know. I show that to some people and they're like, what? Anyway, back to this. Here's my point though. You said 2 angles that add up to 90 degrees. How about this? I'll do you one better. 2 angles that give you a complete 90 degrees. 2 angles that give you a whole 90 degrees. Like 45 and 45 or 30 and 60, something along those lines. Now, complementary probabilities don't add up to 90 degrees. Take a wild guess. Complementary probabilities add up to what? 100. Yeah. So, the general idea is this. The probability, and you may see it written like this. The probability of A with a little superscript of C. It's not an exponent. It's not an exponent, so I don't want to call it that. But it's like a superscript of C. It's A complement is equal to 1 minus the probability of A. Because those 2 probabilities should add up to 100%. Yay! Let me give you an example. Now, let me write this first, and then I'm going to go up to the board and give you a little more detail. Okay, here's the detail. You're taking, let's say, like a multiple choice test or some junk like that. You're taking a multiple choice test. I don't know how many questions there are, but on this multiple choice test, you can get a ton of things wrong. You might get 1 wrong, you might get 10 wrong, you might get 15 wrong. I don't know. but it's somewhere in that range. Like you might get some wrong, you might get none wrong. I don't know. I don't know what it's on. I don't know how many questions there are, but they're all multiple choice. And then the question comes up, okay, what is the probability that you would get at least one wrong? Oh, crap. So it's like, okay, what's the probability that I get one wrong? Or it could be two wrong, or it could be three wrong, or it could be five, all the way up to however many questions there are. Oh my gosh, that seems like a lot of work. And it is. It is a lot of work to try and figure out, okay, one wrong and two wrong and three wrong and four wrong and five wrong. And I have to do something with all those probabilities. Crap, this sucks. Or I could take advantage of the concept of a complement. So hold on, I could do something like this. I'm going to write this in red. I'm going to erase it. Number wrong. I could get none wrong or one wrong or two wrong or three wrong or four wrong or five wrong or six wrong. Let's just say there are 7 questions. If I'm trying to find the probability that at least one of them is wrong, then I'm trying to figure out the probability of one or more. I'm trying to find out that probability right there, the one that I just circled or squared, whatever, rectangled. I don't feel like doing that. So instead, I'm going to take on the concept of a complement. Meaning, if I added up all of these, including 0, that should give me 100%, because those are the only possible things that could happen on a 7-question multiple choice thing. So if I found out instead the probability of getting none wrong and subtracted that from 1, that should give me the probability of at least one wrong, and it will, as long as you're in that kind of scenario. It's called discrete probability. We're going to get into discrete and continuous. Okay. There's a formula that you guys learned way back in the day. I honestly don't remember when you did this. Did you guys ever do like Venn diagrams back in the day too? Okay, a couple people nodding yes, the rest of you staring blankly. Cool, great, awesome. No, but Venn diagrams are very similar to this concept that I'm about to show you. I miswrote it. I want to write it again on a new paper. I miswrote it and I feel bad. Let's do it again. There we go. Notice what I miswrote. Notice what I miswrote. I miswrote that symbol originally. And notice what I just called it. I called it a symbol and not a what? I didn't call it a letter. Normally when you write U's, don't you do that little tail at the end? No? When you write U's, you don't write U's like that? Y'all are weird. You use like this, like that. No. Y'all are weird. Shut up. No, uppercase, look. Anyway, my point is that's not the letter U. It's a symbol. It stands for the word union, but it's not a letter. It's not a letter. No. That symbol, the way that you would read that as the probability of, quote, A or B, end quote. That's how you would read that. A or B. That's the symbol that they use for the word or. I mean, it takes like an extra keystroke just to get in the 2 letters for O and or. But they decided that they wanted to do it that way. All right, we'll do it that way then. Nice. Here's how you calculate it. You do the probability of A plus the probability of B minus the probability of, well, this symbol right there. What the heck is that symbol? What does it kind of look like? A what? A mountain. Nice. It looks like an N, right? But it's not an N. It's also not a mountain. But it's not an N. Don't write it as an N. Don't. Now, when you write an N, do you do that little extra tick mark at the top? Yeah, so you say, no, don't even do that to me. No, but it's not. It's like that upside down U-ish shape. It doesn't mean the word or. It means the word and. Yes. She whispered it and then she was happy. It's A and B. Let me just give you kind of a visual right here with some playing cards. Or playing cards, whatever. Standard deck of cards. How many cards are in a standard deck? Yay, we all did it. How many suits? There are 4 suits. Can you name them? Okay. You've impressed me so far. How many cards per suit? 13. There are 13. There are 13. 13. 2 through 10. And then Jack, Queen, King, Ace. How many face cards? There are 12. A face card is a card with a face. That would be the jacks, queens, or kings. Mr. Markey, do you count aces? No. Do aces have a face on them? No. Come on. Anyway. Now, so if I were to ask you a question, like pick a face card. Pick one face card. King. We'll pick a king. Pick one suit. Spade. Okay, she's just picking everything. All right, cool. So I'm sorry. Now, I wish I set this up beforehand. I have it set up in such a way. Check this out. I don't know why I did this, but like I set it up in such a way where I set up the cards like that. You can see that in the chat right there, where I got like 2s and 3s and 4s and all the fun stuff. I had it set up as suits, but I got a little bored, so I decided like mixing. Shut up. Sometimes when you get bored with like cards and mathematics, you start doing logical things like mixing techniques, and you're like, "Yep, I believe you, Mr. Markey, that you would sit there and just do mixing techniques with playing cards." Yes, I would. But I do have all the kings set up, so they're all the kings. Yay. Okay. So there are 4 kings. How many spades are there? 13 spades. Okay, hold on. And you said there are 52 cards overall? Cool. Let's go over here. The probability of picking a king or a spade from a standard deck of cards, well, the probability of selecting a king would be 4 out of 52, because there are 4 kings out of 52 cards. And the probability of selecting a spade would be 13 out of 52. And you're like, oh, happy day. I don't have to change the denominators, because when you add fractions, you just do that thing. Now, total side note for a second. Mr. Markey, didn't you say you didn't like fractions? Well, no. I didn't say I didn't like fractions. I said I didn't like fractions for what? For my what? No. For let me rephrase. I don't like fractions for what point in the problem? The what? The final one, the final answer. The final answer. Put your final answer at a decimal. It makes sense to leave these as fractions temporarily. But then eventually, once we get our final answer, we're going to convert this to a decimal. Keep that in mind. So 17 out of 52, and we all high-five each other. And then there's those few kids in the class that are like, wait. Look, he's frozen. There's my hand. It's crazy. It's not 17 out of 52. It's not. What's wrong? Why? Where's my thing here? Kings, spades, and smack dab in the middle is the king of spades. Yeah, technically the king of spades has been counted twice. It's been counted once under the king banner, and it's been counted once under the spade banner. But then going with this formula, we should be subtracting the probability of getting a king and a spade at the same time, which there is one card that fits both categories. So we have to subtract 1 out of 52. In this case, getting 16 out of 52, which, don't worry about reducing it. Approximately 0.308 is what it rounds to. I usually like going 3 decimals. Just as a side note, I usually like going 3 decimals. Oh, good. Thank you for asking why. Nobody. Anyway, I like going 3 decimals because if you had to convert that to a percentage, what would be the percentage? 30.8. Usually with percentages, it's good to go a decimal point further on percentages. So if the convergence ever needs to happen, where it's like, oh, well, the problem, let's just say all of the multiple choice questions, the answers are in percentages, well, then it's just an easy, I mean, you don't even really need to think about it too much. Be careful. This is one little tiny, like sometimes I get this and it doesn't happen often, but it's like 50% is like 0.5, right? And then I ask, and then someone's doing a problem and they're like, oh, 5%, 0.5. And then I cringe and I cry a little bit. No, 5% is not 0.5. 5% is 0.05. Please be careful with what you're doing. Now, there are going to be certain instances in which the probability of A and B, this calculation right here, there are going to be some problems where that value is 0. There are going to be some instances where that probability is 0. If the probability of A and B, notice the notation that I used. I messed up the notation again. There we go. Y'all get me messed up with these mountains and valleys. Nobody said valleys. I filled in the gap. I don't know. If the probability of A and B, there we go, and there's that symbol right there. If the probability of A and B is equal to 0, meaning there is nothing that the two events have in common, or it's not possible for both events to happen at the same time, then A and B are, quote, mutually exclusive. Have you guys been taught that before in a previous year of math? Yes. Some yes, some no. Okay. What grade? Really? Crazy. All right. Do you know the other way of saying it? Or we call those events disjoint, as in get me out of disjoint. No, that's not what they mean. Disjoint, I like to think of it as a shoulder that has been dislocated. If you've ever think about a shoulder that's been dislocated, it's disjointed, meaning they're not connected anymore. Think of a Venn diagram that has no overlap between them, meaning you can separate them from each other. They are disjointed, meaning there's no overlap. The probability of A and B is equal to 0. Let's see. Ooh, I found the penny I took out earlier, and I thought to myself, oh, I found a penny. And then I got sad because I'm like, wait, I already own that penny. Gosh. Why do pennies before 1982 weigh differently than pennies after 1982? What material? Nice. Before 1982, they're made out of like 90-something% copper. After 1982, they're made out of 90% something zinc. If you took a penny and bounced it on its end, before 1982, you would hear a little ping. After 1982, you would not hear that ping. I mean, you hear the sound of the penny hitting the thing, but it'd be like you wouldn't hear the echoing ping afterwards. Anyway, fun facts. Let's see what we got here. Now, the probability of A and B. Notice the notation that I'm using here. Notice the notation that I'm using here. There are technically two ways to do the calculation for the probability of A and B. Two ways. First, you could do the probability of A times the probability of B. That's one way of doing it. Now, hold on. Here's what I want you to do. Listen, listen, listen. I'm going to separate this, but I'm going to leave blanks. I'm going to leave blanks because I'm going to write a little bit more here. I'm going to write a little bit more here. I just want you to be aware of that so that you know what I'm doing. The other way of calculating the probability of A and B is this. Look at that symbolage. Look at that symbol. I can't even talk today. Look at that symbolage. The probability of A and B clearly has some kind of multiplication going on between the two terms. Fantastic. You are multiplying the probability of A times the probability of B, but then you have this weird symbol going on in the second calculation. Ooh, what does that look like to you? Kind of. It's not though. I mean, clearly it's not based on all the other symbols I've given you guys today. It's not a division sign. It's not. Kind of. It's a vertical line. How would you read that? Hold on. How would you read that? You'd say the probability of what? B. No. Not at all. Hold on. First of all, you would use this top probability calculation if the events A and B are independent. If they are independent events, meaning that one does not depend upon the previous one happening. Independent events are not affected by the other event occurring, whether it be before or after. They are independent of one another. They do not rely on one another. Whereas, for the second one, you would do this if A and B are dependent. If they do depend on one another, if the probability of B would change based on what happened with A occurring right before it. So, for example, basic example, here's the probability of A. I don't know, would be like a probability of picking a king. Oh, 4 out of 52. Cool. Now, let's say I pick a card, and it just happens to be a 2. I put that card over there on the computer. Now, what's the probability of picking a king? 4 to 51. Now, it changed. The second event depended on that first event. Whatever happened in that first event would change the second event. Again, for example, let's just say probability of picking a king, 4 to 52. Boom, I actually pick a king. Look at that king. There's the king sitting on my desk. Then, what's the probability of picking a king on my second turn? 3 to 51. It changes. It's dependent on the previous events happening. Ah, it's nuts. It's really nuts. No. The line means the word given. 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 Let me write this down. The probability of this, mind you, it is a vertical line. You would read that as the probability of B given A. You would read that as the probability of B given A. Now, I have to write down just one more thing, and then I want to show you a formula sheet from the AP test. And then if we have time, maybe a magic trick. I don't know, we'll see. You just looked at me weird. You don't even know what's happening to me. Anyway. Now, I have to write this down because I want you to see it right here. And I want to show you the comparison. I want to show you the comparison to the formula sheet. The probability of B given A, I should move this up a bit because I just realized y'all are like looking through like bubbles. Move that to the top. There we go. The probability of B given A is equal to the following fraction. And this is just basic algebra if you know what the previous calculation was. Previous calculation being the probability of A and B is equal to the probability of A times the probability of B given A. If I were to divide both sides by the probability of A, they would cancel out, leaving me with this particular formula. Now, the reason why I show you this is for a couple reasons. Number one, it does come in handy because there are certain instances and circumstances in which you would be given the probability of A and B, or you may be able to calculate the probability of A and B, or you might be able to calculate the probability of A, or it's given to you as well. And then they ask you a question like this. Now, I'm not going to do this problem today, but next class, I am going to show you precisely why this formula will come in handy and save your life on a number of occasions. But that's for Wednesday. Now, the second main reason why I show you this formula, and I want you to be familiar with this fraction, is because this thing is how it is presented on the AP test. On the formula sheet, they give you 3 pages worth of formulas. There it is. They give you 3 pages worth of formulas. And right there, at the top of the second page, they begin giving you some probability formulas. And the first formula they give you is the probability of A or B. Probability of A, probability minus probability. And then the second one is that fraction. Now, notice here, they reverse the letters. That's weird. Why do they reverse the letters? I don't know. I've never figured that out. I've never figured out why they reverse the letters. But here's the deal. You always, remember I said the word given before? You always, always, always divide by the probability of the given event. Meaning this is A given B, meaning you divide by the probability of B. On my formula that I gave you, it is still 100% correct because it's B given A, meaning you divide by the probability of the given event. That is how that thing works. I love these formulas. Again, those formulas will be given to you, no pun intended, given to you on the actual AP test, which is nice. I do a magic trick because I can. I've heard this theory about like shuffling a deck of cards perfectly and getting back to the original thing or the original configuration. Theoretically possible, not very likely. So I'm just showing this into the chat right here for all you people. Oh, hold on, let me shuffle them a little bit more because I've taken out certain cards. Okay, I've taken out the kings. All right, just so everyone is on the same page with me, I've taken out the kings and I'm kind of showing them to the people in the chat right there. They're the kings. See all the kings? See all the kings? All the kings are right there. Okay, good. I'm taking out all the kings. Now I'm going to just take the kings and I'm just going to leave them right here, over here. Not touching. Actually, you know what? I'll leave them right here. Anyway, here's the rest of the deck. I got time. And I'm showing the people in the chat just for the fun of it. There's no more kings. I've taken out all the kings. All the kings are gone. They're gone. They're gone. They're gone. Here's the deck of cards. Here are the kings, like I said before. And then chapow, they go right on the top. And this is on video, so you can't, they have to, It's on video. They can rewind anytime they want, right? But then, like, there's a whole story. But you can see there's the first card, pulling it off the top. And I'm putting it in the middle of the deck. Look, I'm showing the people on the camera right there, moving into the middle of the deck right there. There it is. Yeah. Second card. You can see that being pulled off very slowly. Put that in the bottom of the deck right there. That's on the bottom of the deck. And I'm not removing the deck of cards from the camera so they can't claim that I was cheating. I'm just chucking my time right there. And then, and then magically, these kings show back up in the front. It's very strange. I don't know. They're right there. No one's impressed. Whatever. Shut up. Anyway. Anyway. On Wednesday, we are going to pick up with more of this on Wednesday. I am going to deep dive a few things, give you some sample problems, show you exactly why that last formula is such a big deal and how it applies to what we're doing. Now, mind you, this is all of the intro stuff. This is all the intro stuff. This is like formulas that you've been taught in the past, notation that you've been shown before. But I'm going to be showing you a few more advanced techniques as we move forward. And then eventually we're going to be deep diving a lot of probability stuff. I submitted the midterm to my supervisor at the end of last week for this class. And yes, midterm, of course. I'm going to tell you more about that when the time comes. But there will be some probability on that midterm. I'm so excited. Anyway, my bell will be ringing in approximately 3 seconds, so I'm going to sign off this live stream.